Good afternoon, everyone. My name is Huanne Xu. I am from the Chinese University of Hong Kong. Today, my presentation topic is combinatorial multi-arm bandits with concave rewards and fairness constraints. This is joint work with Liu Yang and Professor Wenchong Nao and Li Rui. Multi-arm bandits has emerged as an important framework to model real problems, such as network resource allocation, ad placement, and cross-sourcing applications. Among these problems, one important feature is that multiple arms can be selected in each round or in each time slot. This is so-called combinatorial multi-arm bandits. For example, in wireless communications, multiple clients can be scheduled for simultaneous transmissions as long as the channel can be divided into multiple subchannels by using multiplexing technologies. Another important feature is that each arm requires a certain fraction of selection to guarantee fairness or provide quality of service. For instance, in internet advertising, each ad needs to be guaranteed to allocate a certain percentage of impressions. However, one fundamental challenge herein for this kind of combinatorial multi-arm bandits with fairness constraint is that can we design a computationally efficient algorithm with providing theoretic performance guarantees? Before going to design details of our algorithm, we first review some related works. The first piece of work I want to share with you is combinatorial sleeping bandits with fairness. In this work, authors consider that some arms may not be available in a particular time slot. And this work combines the UCB bound with visual equivalence to trade off the performance of bandit algorithm and also the fairness constraints. However, in this work, no sublinear regret bound can be achieved. The second piece of work I want to share is fair multi-arm bandit algorithm. One fundamental limitation in this work is that only one arm can be selected in each round. Authors extend UCB algorithm with greater fairness, and the first priority is to guarantee the fairness. Once the fairness can be guaranteed, the authors use the traditional UCB bound to select arms. The last piece of work I want to share is contextual multi-arm bandit, its fairness. In this work, authors consider that two arms with similar context need to be selected with similar probabilities. In our work, we design a general framework to model all important features in combinatorial multi-arm bandits. To begin with, we consider that in arms, each arm will generate a random reward once it's pulled. For example, for MI, RIT is reward generated in round T once MI is pulled, and all the RIT from the same I follows a distribution. This distribution is not known in advance. We need to estimate. In addition, in each round, we consider at most M arms can be selected. To guarantee fairness, we assume that within T rounds, each MI needs to be pulled at least T times I times. This I is a parameter specified by each arm. Our optimization goal is to maximize the total rewards pulled within T rounds. We begin to introduce our formulation. In this formulation, The decision variable is xit, denote whether mi has been put in round t. xit is a binary variable. To model the nonlinear effect, we consider to maximize a concave function of the total rewards poured within t rounds. This is a different problem, and existing methods using LP solver to solve the problem. In particular, we will first estimate the reward in each round, and using this estimated reward to replace the exact reward in the objective function, and then solve a linear programming problem, which can be quite complicated. By contrast, in this work, we use a very simple algorithm to tackle the optimization problem. To begin with, we use the function duality to approximate function using the conjugate function. The second step is to apply UCB type estimation on the reward, which is a combination of the empirical average with some bounds with a confidence interval. The most important step we apply is to apply convex optimization techniques to tackle this problem using the two steps in the above. We need to transform the fairness constraint into multiple short-term constraints. By doing this, we then construct a compact set which transforms the binary variable to continuous variables and still guarantee the sum of sections in each round is less or equal to m. By doing this, we perform simple gradient descent algorithm to determine the value of each xt. Since xt may not be binary variables, we then use the randomized routing scheme to turn this xt into integers. By RS sampling, we can guarantee the integer result still satisfy this combinatorial constraint, namely, at most m arms can be selected in each round. It turns out our algorithm can achieve some nice properties. First, it's computationally efficient. The complexity is at most the order of n squared in each round. Moreover, we prove that the fairness constraint can be satisfied asymptotically. More importantly, we can achieve a sublinear regret bound with high probability. To prove this results, we use Ninaplov drift analysis with bandit analysis. The key step is to bound difference between the actual reward with the estimated reward. We show that this difference can be bounded by a sublinear function with respect to time t. After this, we use the traditional convex optimization techniques to bound difference with the optimum value and our achieved solutions. We also conduct simple experiments to evaluate performance of our design algorithm. In this setting, we consider that 100 amps and in each time slot only 30 amps can be selected. Rewards are generated using Pareto distributions. We also adopt two baseline algorithms to compare to our design algorithm. The first algorithm is LP solver. The next algorithm is so-called LFG algorithm, which balance the trade-off between this UCB bound and also the fairness constraint. During this experiment, we show that our design algorithm can achieve both a smaller regret as well as a small violation of fairness constraints. Finally, we also show that our design framework can be extended to include knapsack constraint. In particular, we consider each arm will generate a random resource consumption once it's pulled. And this budget to control the selection of all arms within T rounds. The budget is B. To tackle this problem, we need to modify the original algorithm by constructing another decision set. In this decision set, we incorporate this batch constraint into multiple small constraints in each time slot. And here the CIT bar is estimation of this resource consumption in each round. We still apply also techniques to tackle the problem within the decision set we have just constructed. We also prove that fairness constraint can be satisfied asymptotically in this setting. Moreover, the resource capacity is violated by a small sublinear term. Last, we also prove that we can achieve a sublinear degree bound with high probability. Finally, we want to conclude our work and also point out some future directions. In this work, we prove the first sublinear degree bound for general combinatorial multi-bandit problems with fairness constraint and also with concave rewards. Our framework can be extended to generate concave rewards with knapsack constraints. In the future works, we want to extend our work to tackle contextual multi-bandit problem with fairness constraints. That's all. Thank you for your interest in my presentation.